Circus.
Okay, so we were talking about convection, right? And just to give you a recap, these were the equations. Okay, and this first one is the continuity equation, and as far as these flows are concerned, we are talking about 2D flows, and which are basically steady state. You see there is no partial by partial t term over there, so we are just talking about steady state flows. So this is continuity equation, x and y part of momentum equation known as Navier-Stokes equation. This is the energy equation, and this is something which relates to equilibrium of the species. Okay, and we talked about all these things. You know what is x, this is the source term for momentum equation, y is the same for y part of the momentum equation, q is for the energy equation. Okay, and by the way, you can see those derivations in your book as well. I am talking about Sengel's book. Okay, so I just gave you some introduction about velocity boundary layer, thermal boundary layer, concentration boundary layer. You see there is some similarity or analogy existing between them, and we started solving this problem. Flow between parallel plates. Okay, so, and we were at a point where we, from continuity equation, we came up to a conclusion that u is a function of y only. Okay, and after that we came up with this thing that if this plate is, the lower plate is basically static and the upper plate is moving with a velocity v, right, and these are infinite plates. We have already talked about those assumptions. Now, so you come up with what? Come on, what's the relation? C1 what? Okay, C1y plus C2. So this is the generalized relationship. And to find out these coefficients C1 and C2, you need to impose boundary conditions. Now let's impose the first boundary condition, u at y equals 0, if let's say these are the x's. So y starts from this plate and goes up to this point, and let's say this maximum y is, let's say L, this maximum y is L. So u of 0 is what? It is 0. Why? Because we are talking about the static plate, and then we have y is equal to again 0, so C1 is equal to 0. Okay, is that the case? Oh, I'm sorry, yes. Yes, C2 is equal to 0. Okay, so, and then at y equals L, you have velocity capital V. So you come up with what? C1L. So C1 is equal to what? V by L. It means u of y in this case would be equal to V by L into y. So this is the linear velocity profile. If you plot it over there, you see at y equals 0 and up to a length of, let's say L, you would have u equals v. Okay, so this is how it goes, and the slope of this line is defined by v by L. Okay, and similarly, if you know that those plates are in relative motion, so you can just adjust the velocities and find out the coefficients. So this is about continuity equation, and those relations are coming from the x part of the momentum equation. And the very important thing we talked about in the last class, this what about this thing, that how did we say, right, and this was coming from y part of the Navier-Stokes equation. Okay, so it means that pressure gradient is basically only existing along the x direction. Okay, not in the y direction, but velocity variations are dominant along the y directions. That's what we talked about. Sorry? Infinite plates. Yes. Yes. You do not know whether the flow is. By the way, if those plates are infinite, so can you say that? Yes, you can say that. Why? Because the flow is not due to the pressure difference. Actually, it is because of the motion of the plate itself. Okay, the upper plate. Okay, let's talk about the energy equation. Now we are interested in finding out the temperature profile. This is the actual question as far as this heat transfer is concerned. And I told you what is the application for this particular liquid flow. You remember? We talked about that in fluid dynamics course as well. You remember those piston cylinder examples? I told you if you are talking about flow of an oil, lubricating oil, in a piston cylinder assembly. Okay, these are just like parallel plates. So that piston may be acting as what? The static plate, and that the cylinder, and that piston may be acting as the moving plate. Okay, it is just like fluid flow. So you can say that this is basically this is happening in reality. So this is a good approximation in those cases. Now, but obviously that oil is basically a non-Newtonian fluid. Remember that there is a limitation as well. Whenever you look at the application, you should know what is the limitation you are dealing with. So in this case, whenever we derived that Navier-Stokes equation, we come up with what? We come up with the Newtonian flows. Okay, but in specifically for oils or lubricating oils, those are generally non-Newtonian flows. Okay, so you have to do certain kind of modifications in the governing equations. But anyways, my point is just to give you an idea how you approximate the things as an engineer while you are working on these things, and then you should know the limitations as well. So let's talk about the temperature profile. So for temperature profile, we would only be looking at energy equation. Okay, so let's see what energy equation says. Just look at this thing. Remember, we are talking about isothermal plates. So let's see what are the terms which are beneficial for this purpose, which are required to find out the temperature profile. Just look at that. This rho Cp, these are the material properties, no problem at all. We need to look at the other terms. Is there any kind of source term? Not at all. So let's disregard this thing. Let's talk about this term, U partial T by partial X. Now U is significant. U is significant. What about partial T by partial X? Why? Because we are talking about isothermal plates. You remember, we are talking about this arrangement where X is the horizontal axis. If this whole plate is isothermal, it means this plate is getting a temperature of T1 and this plate is getting a temperature of T2. So is there a temperature gradient along X? The whole plate. I am just talking about the whole plate. So it means this partial T by partial X term is the whole. Why? Because if this whole line, if this whole plate is at a temperature T2 and this whole plate is at a temperature T1, so you can say that within the flow, within the whole domain, this partial T by partial X would be kind of immaterial, right? And then let's talk about this term, this V partial T by partial Y. Now obviously partial T by partial Y would be dominant. Why? Because there would be a variation along Y in temperature, but there is no variation in V, right? So this term would be disregarded by virtue of either V or partial T by partial Y. So this term is disregarded by virtue of V, very small vertical velocity. Then if partial T by partial X is very small, partial square T by partial X square is obviously, right? So this term is again disregarded. So can you say anything about this term? Not at all. So it would stay there. Now this mu into phi term, let's see, this is mu into phi term. So partial U by partial Y is what? You have already found out that U is equal to what? V by L Y. So partial U by partial Y would be equal to V over L. So what about this partial V by partial X? We don't need to look at that. Why? Because partial v is very small, so there is no variation of v with respect to x. And what about this thing, partial u by partial x? U was only a function of y by continuity equation. We proved that. So partial u by partial x is again 0. And what about this thing? This is also neglectable. So we come up with only these terms, few terms, and those few terms are zero. If you remember that left hand side was 0, and then we come up with that k partial square t by partial y square plus mu partial u by partial y whole square. Okay, just see that we come up with these few terms. Now what is partial u by partial y? V over L. So this is k partial square t by partial y square plus mu v square over L square. So you come up with partial square t by partial y square equals minus mu over k v square over L square, right? And then I can say this partial t by partial y, let's integrate it. So you would come up with minus mu over k v square over L square y plus C1. And if you integrate it once again, so you come up with this temperature as a function of y, and that would be mu over k v square over L square y square over 2 obviously. Then you would have C1y plus C2. Okay, so this is how it is. So this is the temperature profile within the oil region or within the fluid region if you consider quiet flow. Okay, so velocity profile was linear, but temperature profile is quadratic. Okay, this is quadratic, square. Now we need to find out the C1 and C2. We have already assumed. Let's talk about those boundary conditions. Temperature at y equals 0 is T1. At temperature at y is equal to L is, let's say, T2, right? So just plug in the value into those equations and give me the value of C1 and C2. Come on, what is C1 and what is C2? This is quite straightforward. If you just plug y equals 0, so C2 would be equal to T1. Yes, C2 would be equal to T1. Just give me the value of C1. You come up with that C1. What was that? 1 by L. T2. Okay. I'm sorry. Just you can speak. T2 plus mu. Okay. Okay. Okay, are you sure about that? What is that? Come on, you just need to find it out. Minus? Is that there? Okay, minus T1. So we have come up with this C1 and C2 value. Okay, just plug those values. Just check whether it is correct or not. I hope it is correct. Just plug those values back into this C1 and C2 and come up with the final expression. And remember, this expression, this is very important to understand, that this expression, once you put those two relationships back into this general solution, you come up with the particular solution for what kind of boundary conditions? Only isothermal boundary conditions. Like for example, if I give you a problem where I say that this plate is at a temperature T1, let's say, but on this plate you have Q dot conduction, let's say I just specify the temperature gradient or flux, for example. I just say it is 2 units, for example. Yes, then what would you do? You need to find out those coefficients accordingly. Remember that. Okay, if I specify flux instead of that temperature condition on some of the plates, so you should remember that this particular solution would not be applied to this problem then. So you need to find out those coefficients according to those conditions. Okay, and you already know that what is that Q dot. You can just find it out using this expression. You can put it like 2 units and find out this dt by dy, and you know how to implement that. What kind of condition it is? Dirichlet or Neumann? Neumann condition it is. Okay. So, any question about this thing? Sorry? Oh, I'm sorry. Yes, this should be, I'm sorry, this should be dt by dy. dp by dy. Why? Because you are only considering temperature varying in the vertical direction. So that flux should be crossing the surface, isn't it? If this surface is like this, so this flux should be normal to the surface. So if the plate is vertical, then you can say it is normal to that surface would be like dt by dx. Okay. Any other question? I hope you understand the intricacies which are associated with those boundary conditions. Any question? Okay. So, because we are talking about the introductory stuff for the convection, I would introduce few of the non-dimensional parameters now. And you already know by virtue of that Buckingham pi theorem, you remember that we derived those pi terms and we come up with few of the non-dimensional terms which are known as pi products as well. And I told you at that time that generally whenever you perform experiments, you describe your results in terms of non-dimensional variables. Okay, and there are so many advantages of this technique that you can not only reduce the number of variables which are affecting your system's performance, but that applicability range is also increased. Applicability range. Like for example, if someone is performing some experiment with a cylinder of, let's say, 2 centimeter diameter, and you start performing that experiment by a cylinder of diameter, let's say 1 meter. So by virtue of those pi products or similarity variables, you come up with the similar results if your Reynolds number remains the same, and if you talk about the compressible flows, your Mach number also should remain the same. Okay, so this is the advantage, that if you perform the experiments in this region of the country and someone is performing the experiments in, let's say, Europe, so you know how to correlate the things. Okay, so this is the advantage. I told you that in convection there are 2 coefficients which are very important. One of them is the friction coefficient, that itself is a non-dimensional parameter that comes by non-dimensionalizing shear stress, wall shear stress, and you non-dimensionalize that shear stress by dynamic pressure. Okay, so that is Cf. And the second important coefficient is convection coefficient. So that convection coefficient is a dimensional parameter, right? So to make it non-dimensional, we have a number which is known as Nusselt number. Okay, again these numbers are basically defined with the names of those scientists who proposed those numbers. Okay, so Nusselt was a scientist who basically proposed these kind of things, and Nusselt number is defined as this thing. Okay, so I would just explain those things. Don't worry about it. I just copied it from the book and just pasted it over there just for my own reference. Just look at this thing. How do you define this Nusselt number? This Nusselt number is defined by h, which is required to be non-dimensionalized. Then you multiply it with the characteristic length. Now this is the characteristic length, remember that. And you remember that for bluff bodies you use diameter as the characteristic length, and for plates or let's say the airfoils you use the chord length. Okay, and then this is thermal conductivity. So you can non-dimensionalize h by multiplying it with the characteristic length and divided by thermal conductivity. Now see, how do you relate those things? For example, this is basically, this defines convection and this defines what? Conduction, isn't it? In the numerator you have convection, and in the denominator you have conduction. So you can say that Nusselt number is a measure or is a ratio of convection and conduction, right? Just see, these two expressions says, for example, you have a plate, you have some plate, and the layer of fluid which is sticking with that plate, that would have the heat which is being transferred from the plate to that particular layer through conduction. Why? Because there is no motion of that particular fluid layer which is sticking with the plate. So that is basically transferred by conduction. Okay, so here you can say that this Q dot conduction can be written as K delta T by L, right? K delta T by L. That that layer, I am just talking about that layer which is very close to the plate. Okay, and then you already know that for the rest of the stream, this particular layer would be transferring the heat to the rest of the free stream. Okay, and that's how that thermal boundary layer would develop. And because the upper layers, they start moving with some velocity, so you define this Q dot convection as H delta T. Okay, now you know that process starts from here, and this heat would be then transferred into the next layers through convection. Now I need to put them equal to each other. I can put those two things equal to each other, or I can take their ratios as well, right? Now if you take their ratios, you would come up with this definition of the Nusselt number. So what is this thing? Physically, it describes the heat transfer rate or heat flux when you have some motion in the fluid relative to something when you have no motion of the fluid. I repeat, you see, this is a ratio of Q dot convection and Q dot conduction. Now Q dot convection is happening when you have some motion of the fluid, and Q dot conduction would be happening when you have no motion of the fluid, isn't it? So if I say that this is equal to 1, this ratio is equal to 1, what does that mean? Is there any motion in the fluid? Not at all. Why? Because Q dot convection is exactly equal to Q dot conduction. It means whatever is transferring to the next layer, it is only because of conduction. It is only because of conduction. For example, if this value becomes much greater than 1, what does that mean? That Q dot convection is much greater than Q dot conduction. So then you have certain advantages of associating the convection heat transfer mechanism in your application. Okay, generally you would find all of the system performance in terms of Nusselt number. Whenever you report your results, in generally I think in the industrial manuals as well and in the research papers as well, you find that your results would be, the performance of the convective mechanism would be defined by Nusselt number, and if that Nusselt number is greater than 1, then it would be advantageous. Okay, if it is equal to 1, it is close to 1, then it is kind of no relevance whether you have some motion of the fluid or not. Sorry? I repeat, Nusselt number is there to non-dimensionalize what? Convection coefficient. Okay, we generally see all the results, all the system performances in terms of non-dimensional numbers, and you already know what is the advantage and what is the importance. Now the basic objective is to non-dimensionalize H. Okay, now I come to the definition of the Nusselt number, that how to read the result. For example, how to read the value of the Nusselt number. If in some document it is written that Nusselt number for this particular flow is like 1, what does that mean? You already know that Nusselt number is a ratio of what? Q dot convection over Q dot conduction. If it is equal to 1, it means whatever is happening over there, that is not due to the fluid motion. If you have installed some kind of fan, let's say you are basically giving some kind of electrical energy to run that fan, and it is not giving you a Nusselt number of greater than 1. or much greater than 1. So is there any advantage of applying that motion, let's say the energy source in that application? Is there any benefit of that fan? Not at all. I mean, you are wasting your electrical energy. Okay, so in this way you always think about the value of the Nusselt number, that it should be greater than 1 if you have some motion of the fluid. So that's how you can read the results. Energy conservation is what? So you know what is Nusselt number now. Okay. Now let's talk about another non-dimensional number, which is the PRANTTL number. This is the definition of the PRANTTL number. PRANTTL number is a ratio of molecular diffusivity of momentum and molecular diffusivity of heat. This is the kinematic viscosity, which defines that molecular diffusivity of momentum, and this is the diffusion coefficient, that alpha thing which you have seen in the conduction studies. So this is nu over alpha. Once you plug in their values, you come up with this thing, mu Cp over K. Okay. Now, okay, let me write it down over there. Just see. For example, if alpha is bigger, you would say that heat would be diffused at a faster rate. If mu is large, you would say that the effect of friction would be propagated at a faster rate. Okay. Now see, what is the advantage? Basically, this parameter defines the relative thickness of velocity boundary layer and thermal boundary layer. This PRANTTL number defines the relative thickness of velocity boundary layer and thermal boundary layer. Just see. This parameter controls this new thing, or this mu thing, this viscosity, that controls the boundary layer. Which one? Velocity. This alpha, the diffusion coefficient, heat diffusion coefficient, that basically controls the thickness of thermal boundary layer. Okay. Now if I say, if PRANTTL number is less than 1, alpha is bigger than mu, isn't it? If PRANTTL number is less than 1, the term in the denominator should be larger, right? Now if PRANTTL number, you have this value of PRANTTL number, what would you say about the thickness of the boundary layers? Would you have thicker velocity boundary layer or thicker thermal boundary layer? Thermal boundary layer, right? So if you have PRANTTL number less than 1, it means what? Thermal boundary layer is thicker. If you have PRANTTL number greater than 1, it means velocity boundary layer is thicker. And this thing is associated with few of the applications where you need this K. This K in the denominator says that if you want to have some application where, let's say, you need to have more thermal conductivity, then you should choose such a material which has lesser PRANTTL number. You see, all of them are material properties, isn't it? All of them are material properties, right? So you need to look at your requirement, whether you need higher thermal conductivity, or let's say, because all of those boundary layer things are basically not relevant to, particularly to the industrial things. Whenever you are talking about some application in industry, and you just need to decide whether you need to use this oil, or let's say this lubricant, or for example this particular fluid, that may be liquid metal as well. So what you need to do, you just need to look at the practical aspect, whether you need higher thermal conductivity, you need to have, let's say, viscous flows, you need to increase the velocity, what you need to do, and accordingly you would choose that particular material. Okay, so if you need to have more heat diffusion, more thermal conductivity, stronger thermal conductivity, then you need to choose those materials which are having what? Prandtl number lesser than 1. I mean, you would have those tables with you. Generally, that data is mentioned in those terms. Okay, so just look at that and look at the physics of those numbers. So this is about the Prandtl number. This mass transfer is what? Not particularly. For example, if there is a plate, so is there any kind of mass transfer then? If there is a flow of air from a plate, can you be a little louder? You need to what? Okay. Okay. No, you can have, like, I am just talking about, for example, there are so many applications. For example, there is very interesting example given in your book. If you see that paragraph in Sanjal's book, he explained why do you want to use liquid metals as the conductors, or to take the heat away from whatever wherever the reaction is going. So you need to take the heat away by the liquid metals. Why? Because you have very small space. You need to conduct the heat very efficiently, right? And you use the liquid metal. You don't use any kind of oil over there. Okay. By giving some values in that paragraph, he explained that concept. Prandtl number greater than 1 for, obviously there would be a Prandtl number if you have heat transfer. The only thing is whether you need to diffuse the heat quickly, or you need to diffuse the velocity quickly, or friction or viscous effect quickly. You understand that these are the two things where you need to decide about. Sorry? You need to keep the velocity very low. But the question is to what extent? Right? If you use a liquid metal, or let's say you use water, or let's say you use oil, they have different mu's. Or even if you want to use a gas, they have different mu's. Okay? So which one would be more viscous? For example, if I ask you which one would be more viscous, you need to look at the value of mu then. It is not the value of K then only. So there are so many parameters which are coming in, and then it is not only the Prandtl number, C. You would also be looking at CF. You would also be looking at the cost of the liquid as well. Right? So there are many things. We are only focusing those particular parameters, which is basically Prandtl number, mu, and then K. Is there still any question? Sorry? This is not V, this is mu. Mu. Yes, mu. It means diffusion of friction. Now what is meant by friction? Diffusion of friction. It means if this is the plate, if you have a greater mu, so you would have what? Your boundary layer may be coming at this point. If you have a lesser mu, your boundary layer may be coming at. You understand that? So that's what I am talking about. If you have more boundary layer, obviously your friction coefficient would also increase. So obviously to get the fluid flow moving, you need to install some energy source as well. Okay. Any other thing? Okay. Just this one question. This is an example. I have taken it from your book so that you understand how to find out those parameters. During the flow of air at T infinity equals 20 degrees centigrade over a plate surface maintained at a constant temperature of Ts is equal to 160 degrees centigrade, the dimensionless temperature profile. Now you see, this is the dimensionless temperature profile. Ty minus T infinity over Ts minus T infinity. Where did we use that parameter to define what? Thermal boundary layer thickness. Okay. This expression is given to you. Obviously that can be measured experimentally, or let's say numerically through CFD, and the value of this A is given, and Y is the vertical distance measured from the plate surface in meter. You see, this is the temperature profile which is given. You need to find out heat flux on the plate surface. Now, what do you mean by heat flux on the plate surface? Whether it would be conductive or convective. On the plate surface, it would be conductive or convective? Conductive, right? So it means at y is equal to 0, this would be what? Your required heat flux. And how can you find out this value? You need to differentiate this term. You need to differentiate temperature with respect to y. Every other thing would be taken on the right hand side, and you need to differentiate it with respect to y. You need to put y equals 0 and then multiply it with k and come up with the answer for this heat flux. And what is the convective heat transfer coefficient? You remember that we talked about its definition in the last class. How can you find out H? Come on. You remember where we put them equal to each other, right? That was something which you were talking about earlier. Why? Because all the next layers would be getting heat from this first layer. Heat would be transferred from here to here. Okay. So, any question? And by the way, I just want to add to my comments on your question, where you said that Q convection cannot be larger than that Q. That particular conservation of heat principle is basically, it is about you. I think there is a confusion. You were talking about the amount of heat. I was just talking about the rate of heat transfer. The rate of heat transfer. Why? Because just see. For example, if you just try to plot this partial t by partial y term at y equals 0, isn't it? So this is the plot. Okay. So is it the same everywhere? So you can't say that. I mean, that we were talking about the rates at that time. We were not talking about the amount of heat transfer. So that was the confusion. Anyways, so this is the last point of this lecture, although this last point is also requires some elaboration. Have you ever heard about yes, you might have heard about it from fluid mechanics, Blasius. Now, what he did was, by the way, this Blasius was a scientist. He defined those relations which we are going to talk about in his PhD, during his PhD. Okay, and those relations are very important in convection studies or in fluid dynamic studies. And these solutions are also known as similarity solutions. Have you ever heard about this PRANDTL? You remember? So PRANDTL was a PhD advisor of Blasius. He was Blasius' PhD advisor. Okay, he did all those things during his PhD, those similarity solutions, and still those relations are used. Okay, so what was the problem? The problem was to find out that boundary layer thickness, or let's say the friction coefficient or the convection coefficient for flow over a flat plate. That was the problem. Okay, and you have non-linear equations, isn't it? Partial u by partial x plus partial v by partial y equals 0. This is the continuity equation, and then you have Navier-Stokes equation. These equations are non-linear. You can't solve them analytically. Blasius assumed few things. He assumed that the flow is laminar. He took it as कुछ ना कुछ चलता ही रहता. And then you have steady state, right? And generally, to keep the things very simple, he took it like 2D, right? Now, what he did was to find out the velocity profile. You remember that this friction or shear stress is dependent on the velocity profile. You need to take partial u by partial y, and for h you need to take partial t by partial y. Okay, it means you have to solve those Navier-Stokes equation first, and then you can come up to those expressions. You need to have that u term, then you need to have temperature profile, then you can take their derivative with respect to x or y, and then you can come up with their definition of Cf and h. Right? So what Blasius did, he somehow or the other, I am not going into the technique which he adopted, we can talk about that technique in a graduate course. I am just giving you a hint. These are partial differential equations. Right? These are partial differential equations, and if you only talk about the velocity profile, you need to solve three equations. Let's say the continuity or the two Navier-Stokes equation, x and y part. You need to solve those equations simultaneously. These are partial differential equations. What Blasius did, the strength of his technique is he converted those set of partial differential equations into a single ordinary differential equation. Okay, he converted Blasius. His work basically that was composed of the conversion of this PDE set into a single ODE. Okay, how did he do that? I am not going to talk about that, although there was a small paragraph written in your book. You can also read that, but I don't want you to indulge in that similarity solution. This was the crux, that convert that set of partial differential equation into a single ordinary differential equation. But there is again a complexity, that the single differential equation is non-linear, so you can't solve it analytically. This single ordinary differential equation becomes non-linear and you can't solve it analytically. What he did was, instead of using those variables partial u by partial y, sorry, u and v, his independent variable was only eta, right? And you can say that this eta is kind of non-dimensional y. Non-dimensional y. This eta is kind of non-dimensional y. I am just giving you the physical significance of all the parameters which he used. And then he came up with a function of eta as well. Right? So in his ordinary differential equation, this was the dependent variable and this was the independent variable. So you can say that instead of x and y, he chose eta only, and instead of having u and v as the dependent variable, he has some function of eta. Now what is that some function of eta? That is just about mathematics. Right? Now using this approach, he came up with few relationships. I don't want to, again I repeat, I don't want you to get yourself involved into those derivations. You just need to look at the result, and that those results says he came up with these expressions. He said that velocity boundary layer thickness, again those assumptions, take care of those assumptions, laminar, 2D and all those, steady state. So he said delta is equal to 4.91 over v over mu x. And what is this v? This is the free stream velocity. So you see, for example, if I just try to plot the velocity boundary layer thickness on a plate, so this is v, the fluid is having a kinematic viscosity of nu, and this is increasing x. Now if you have increase in x, you have increase in boundary layer thickness, right? You have increase in boundary layer thickness. So you can convert it into Reynolds number, local Reynolds number. You see, it is dependent on x. So you have this relationship 4.91 x over under root Reynolds number x. This is basically local Reynolds number. I have already explained what is a local property. And as far as that shear stress is concerned, wall shear stress, he gave us these relationships. I have given you the approach, how he did that, what kind of approach he used, and then without going into the derivation thing, I am just coming up to the conclusion part. What was his conclusions? Conclusion was these things. He gave us the value of velocity boundary layer thickness, he gave us the value of the wall shear stress, and then By non-dimensionalizing this wall shear stress, he came up with this thing. And look at the beauty. Look at the beauty that all of those parameters are functions of Reynolds number. You understand that? Now it does not matter you have a bigger plate or a smaller plate. It does not matter whether, as long as you are operating in a certain range of Reynolds number, your flow remains laminar. So still you are good to use those relationships which were defined by Blasius. Okay, so we would start from this point onwards in the next lecture, inshallah. Thank you.